Hello friends, in this video we are going to discuss about the MOS capacitor with p-type substrate. So for that MOS capacitor, we know that MOS capacitor is the heart of MOSFET, and these MOS capacitors are generally of two types. If the MOS capacitors is fabricated using p-type material or p-type substrate, then it is called MOS capacitor using p-type substrate, and this MOS capacitor is also can be fabricated using n-type substrate, then that MOS capacitor is called as n-type substrate MOS capacitor. So now we are going to investigate into the p-type substrate MOS capacitor. So for that, let us analyze what is a capacitor, then we will go to the MOS capacitor. For this, MOS capacitor can be explained using the parallel plate capacitor. So we know that the parallel plate capacitor can be drawn in this fashion. So it is one plate, another plate will be there. So this is another one metal plate, and in between the metal plates a dielectric material is given, and this is the dielectric material. So I can call it as a dielectric material, and this is the metal plate, and this is also the metal plate. Now there will be some electrical connection given to the metal plates. So this is the basic block diagram of a parallel plate capacitor. Now if we give a negative potential to this up metal plate and positive potential to the down metal plate, then we can say that negative charges will accumulate on the above metal plate and positive charges will accumulate on the below metal plate in this fashion. Now there will be an electric field created inside the dielectric material in the upward direction, and if the distance between the two metal plate is small d and epsilon is the permittivity of the dielectric material, then we can say that the capacitance of the capacitor will be capital C is equals to epsilon A by D, where A is the cross sectional area or the area of the metal plate. Now from this equation we can find the value of capacitance of this parallel plate capacitor. Now if we find the value of capacitance per unit area, can be defined as C dash, then it will be C by A, that means epsilon by D. Now we can see that this is the capacitance per unit area, and from this we can find the magnitude of the charge per unit area of the capacitor plate will be equals to Q dash, that is C dash into V that has been applied. So magnitude of the electric field can also be found that is existing inside the dielectric material. And this will be equals to capital E is capital V divided by the distance between the two plates. So this is all about the parallel plate capacitor, and using this parallel plate capacitor concept we can explain the MOS capacitors. And for a p-type MOS capacitors, the structure of p-type MOS capacitors will look like this. So this will be the p-type substrate, and on the p-type substrate silicon dioxide will be grown. So this is the silicon dioxide and this is also silicon dioxide. So this is the silicon dioxide and this is the p-type material, and here a metal contact is grown in this fashion. Similarly, a metal contact is grown in this fashion on the silicon dioxide. So this is a capacitor where this is the metal plate and this will act as a metal plate. Now this p-type substrate where there are so many holes inside the p-type substrate, this p-type substrate along with the metal will serve as a one metal plate, and this metal connection will serve as a one other metal plate, and in between the silicon dioxide is there, and this silicon dioxide will serve as a dielectric material. That means we can say that this part of this will serve as one metal plate and this part will serve as another metal plate, and this region from here to here will serve as an dielectric material. In this way, this structure of p-type substrate along with the silicon dioxide can serve as a parallel plate capacitor. So let us see how this parallel plate capacitor operation comes in place inside this p-type substrate MOS capacitor. So let us take a block diagram of a p-type substrate MOS capacitor. So this is the block diagram of a p-type substrate MOS capacitor where this is the p-type substrate, this is the metal. So this will also be the metal, and in between these the dotted region is the silicon dioxide which will serve as the dielectric of the capacitor. Now let us connect a negative potential to this terminal and a positive potential to the metal terminal. That means let us connect a potential in this fashion that the positive terminal will be connected here and the negative terminal will be connected here. So now this is the p-type substrate MOS capacitor that has been given an external voltage. After giving this voltage, we know that inside the p-type semiconductor there are so many number of holes will be present inside the p-type substrate. Due to the application of this positive potential, these holes will face some force which will take away from this terminal, that is, the holes will be attracted towards the interface of silicon dioxide and p-type material. Now these holes, when comes to this interface region, so this is the interface region. So due to the application of the potential from the outside, the holes in the p-type semiconductor will be attracted towards the interface of the silicon dioxide and p-type material at the interface. But the holes, when come to the interface, they cannot move into the silicon dioxide. So they can accumulate. So they will accumulate at the interface in this fashion. So we can say the concentration of the holes at the interface region will be very high compared to the concentration of holes in the region away from the interface. So we can write that hence the interface region semiconductor will behave as more p-type than the semiconductors which are away from the interface. This total diagram can be simplified in such a way like this. So I have drawn this diagram, previous diagram, this one, into a simplified diagram like this way, where I have given a metal here. So this is the silicon dioxide layer and this is the p-type substrate. Now previously we have given a positive potential here and negative potential here. That's why a electric field will be created from this positive potential to the negative potential through this dielectric material. Due to this produced electric field, since it is a p-type substrate, the majority carriers of the p-type substrate, that is holes, will be attracted towards the interface region and they will accumulate at the interface region. In this way, the holes will accumulate at the interface region. That's why this situation is called accumulation of holes. Now, before the application of the outside potential, if we draw the band diagram inside the MOS capacitor, it will be look like this. this will be the EFI, that is the intrinsic Fermi level, and this intrinsic Fermi level will be at nearly the middle of the band gap. So this is the valence band of the p type, and at same distance from the EFI we will have conduction band of p type, and the Fermi level of the p type will be near to the valence band. So this is the EFP. So this was the band diagram before the application of the external potential. Now let us apply a potential of negative here and positive here, and this is the SiO2 and this is metal and this is p type semiconductor. Now since we have applied a external potential in this pattern, so some holes will be accumulated near the interface. So this region is the interface where a layer of holes will be created due to the electric field capital E created by the external voltage inside the semiconductor. So in this region of interface there will be a large concentration of holes inside the p type substrate. That's why the Fermi level or the EFI and the EVP will bend towards the EFP in this manner. So I can say that at the interface region will be more p type than the other region. So the gap between the EFP and the EVP will be decreased in the interface region, hence the band EVP will be bending in this fashion, and the EFI will also bend according to the EVP like this fashion, and also the conduction band will also bend according to the bending of valence band. So at the accumulation mode of the MOS capacitor there will be a band bending of valence band towards the Fermi level of the p type at the interface region due to the accumulation of holes at the interface. Now we can say this band bending has been accumulated due to the so many accumulation of holes in this interface region. So I can write it as accumulation of holes at the interface. So accumulation of holes in a p type substrate MOS capacitor happens due to the application of this type of external voltage. Now we will inverse the external applied voltage and we will see what will happen if the external voltage will be reversed. So let us reverse the external voltage. So after reversing the external potential in the MOS capacitor, the block diagram will look like this. Now we have applied a positive potential at here and negative potential here. Hence the electric field that will be created inside the MOS capacitor will be directed from this metal plate towards the negative terminal, and due to this electric field, the holes that are residing inside the p-type will be experience a force to move away from the interface. So we can say that now holes will experience a force to move away from the interface. So we can say at the interface region there will be a scarcity of hole, that means there will be a very less amount of holes because the holes has been driven away from the interface region, and that's why there will be remain some acceptor ion like this, and we know that these acceptor ions are the negative charges, and these negative charges of the acceptor ion will serve as the negative charge at the interface region, and the interface region is this one. So we can say now the interface region will behave as less p type than the other regions. So after applying the reverse voltage, we have seen that at the interface some space charge region has been created or some depletion region has been created at the interface of the MOS capacitor just under the silicon dioxide. That's why this mode of operation is called the depletion mode. Now let us draw the band diagram of this depletion mode of MOS capacitor. Now before applying this potential, we know that this is a p-type material, so the Fermi level or the band diagram before applying this potential will look like this. So EFI, that means intrinsic Fermi level, will be just near the middle of the band gap, and this is the EVP, and this is the ECP, and the Fermi level is near the valence band, so EFP. Now when we have applied a reverse potential, then we have seen that near the interface a space charge region has been created, and in this space charge region negative acceptor ions has been accumulated. Due to this negative acceptor ion, the interface region will be now less p type, so we can say the interface region will be now less p type, that is the gap between the Fermi level of the p type and the valence band will now increase due to the application of the reverse electric field. So we can draw the energy band diagram in the interface region like this way. There will be a bending of the valence band away from the Fermi level in this way. Similarly, the Fermi level of the intrinsic semiconductor will also bend according to the Fermi level, and the conduction band will also bend according to the valence band. So this type of band bending will happen right now when we apply a positive potential here and a negative potential here, due to the negative acceptor ion has been created under the interface of the SiO2. Now we have told that this is the depletion mode. Now if we increase the magnitude of this reverse potential, that means if we increase the potential, if we increase the negative potential further, then large amount of negative charges will start to accumulate. That means now negative charge region, that is the interface region, will be wider now, and also the concentration of the negative charges will be also increased. That means the interface region or is now will have more space charge region. That means there will be more depleted acceptor ions in the interface region. That means we also can say that the interface is now is very less p type, and it may that it can be converted to the n type also, because if the Fermi level of the intrinsic semiconductor comes more down, then it can be converted to the n type also. So let us see what will be the band diagram in this condition. That means we have seen that due to the application of more reverse voltages here, the space charge width has been increased. So we can say when a large positive potential, when large positive potential will be applied, to the p-type semiconductor terminal, then we can say that induced electric field, that is the induced electric field E induced, will increase, and the corresponding positive and the negative charges or corresponding negative acceptor ions will accumulate in more numbers. That's why the width of the space charge region at the interface will increase, and band bending or the bending of the bands will be more, and then the conduction band will be more closer. You can look, and the conduction band, that is CB, will be more closer to the Fermi level of the p type, that is EFP, compared to the valence band. That means we can say that at the interface region, the semiconductor has been converted to N type from P type. That's why this mode of operation is called the inversion mode, and the block diagram will look like this. So, this is the block diagram or the band diagram representation of the inversion mode, and in the inversion mode we have applied a large positive potential here and large negative potential here. So, a large amount of electric field has been created in this direction, and that is why a large amount of holes has been moved away from the interface, and that is why a large amount of acceptor ions has been accumulated near the interface, that is denoted by this green line. That is why these negative charges or the negative acceptor ions will provide as the negative charge near the interface. So, this region of interface is now very less p type compared to this region, and eventually the bending of the bands is now more, that means it is more p type and it is less p type. That is why the gap between the EVP and EFP has been increased by a significant amount, and at the interface we can see the gap between the conduction band minima EC and the EFP is this amount, but the gap between the valence band and the Fermi level is this amount. That is why we can say that within this interface region the semiconductor has been inverted from p type to n type. That is why this region is called the inversion layer has been created, and this inversion layer has been created within the distance. Let us denote it as x dt. So, x dt is the thickness of the inversion layer, and this is the band diagram of inversion mode. That means negative charges has been accumulated here, and these are the called as inversion layers of negative charges. So, this is the total scenario of the MOS capacitor, and we can see that in the MOS capacitor there are three regions or three modes of operation. The first mode of operation is the accumulation mode, and the second mode of operation is the depletion mode, and the third mode of operation is the inversion mode. So, this is all about the MOS capacitor with p type substrate with three different regions of operation. Thank you.